Let's look at an example of Newton's third law. But before we do that, let's review Newton's third law. Newton's third law says a force applied by body A on body B is equal to and opposite, the negative sign is opposite, a force applied by body B on body A. So a force from body A on body B is equal to and opposite the force of body B on body A. So let's look at an example. So we're given two astronauts are playing ball in space. One astronaut, whose mass is 90 kilograms, throws a 0.45 kilogram ball with a 0.45 Newton force toward the other astronaut. How fast did the astronaut accelerate is what we want to find. So we're looking for acceleration A, subcapital A, and we put subcapital A for astronaut, A for astronaut. So we have some hints here. The astronaut accelerates in the opposite direction to the ball's acceleration. So if the ball is going to be accelerated to the right, then the astronaut is going to accelerate to the left. Remember, we're out in space. So if you're going to apply a force in one direction, then there's an equal and opposite force in the opposite direction. Use Newton's third law, use Newton's second law where appropriate, substitute on either side of the equation for Newton's second law, and then solve. Expressing your numeric answer, in other words, an answer with no units, in two decimal places, such as 12, 1.2, 0.12, or 0.012, rounding appropriately. Notice that 12 is just two digits, 1 and 2. 1.2, two digits, 1 and 2. 0.12, two digits, 1 and 2. 0.012, still two digits, 1 and 2. You only count the zeros to the right of the number, and since we don't have any digits, any zeros to the right of 1, 2, there is still only 1, 2, 1 and 2 as our number of decimal places, which is 2. So we're going to draw our picture here. We have our astronaut labeled capital A. The astronaut is throwing a ball of mass 0.45 kilograms to the right. And so we have acceleration of the ball as written in red. Now the astronaut, when the astronaut throws the ball to the right, the astronaut is going to respond by accelerating in the opposite direction. So we need to put an acceleration here of the astronaut in the opposite direction. And we're going to give it a little vector symbol because I can't bold it. A vector symbol means that we just need to give it a direction. So let's start solving this problem. We need to start by writing down Newton's third law. So remember, let's review it. Force of body A on body B is equal and opposite to force of body B on body A. Well, we have two bodies. One of them is a ball, one of them is an astronaut. So the force applied by the astronaut, capital A, on the ball, small b, is equal and opposite. Opposite means the negative sign, to a force applied by the ball, small b, on the astronaut. So we're going to carry the equal sign down. Actually, we'll do that in the next step because we want to then, step 2 is substitute in for the second law and solve. So I'll just erase this. So we want to substitute in for Newton's second law. So I'm going to carry the equal sign down. Newton's second law is ma. So we know we want to put an m here on both sides. And we know we want to put an acceleration in here on both sides. And we know one of them has to be negative. We're carrying this negative sign down. So now we need to find out what is going on. So here is the force of the astronaut applying to the ball. So this is going to be the mass of the ball. So I'll put a little sub b here. And this is going to be the acceleration of the ball, so I'll put a sub b. And this side is going to be the mass of the astronaut that's going in the opposite direction, sub astronaut, capital A. Now we just need to substitute in for values. We know the mass of the ball. The mass of the ball is 0.45 kilograms. So we need to put in here 0.45 kilograms. And I'll put parentheses around it. and we want to know the acceleration of the ball. Let's stop right there for now because we don't know that. But we're going to now put in the mass of the astronaut, which we know is 90 kilograms. And then we need to put in here the acceleration of the astronaut, which is what we're trying to solve for. So I'm just going to put that here. So we're solving for acceleration of the astronaut, but we don't know the acceleration of the ball. So let's go back up and find out what we're given. We are given a 0.45 kilogram ball and a 0.45 Newton. We didn't do anything with this 0.45 Newton yet. So we're just going to go on the side here. The force that is applied onto the ball has got to be equal to the mass of the ball times the acceleration of the ball. And since acceleration and force are vectors, meaning we need to provide directions, I'll put a little arrow on top. Now we know the force applied to the ball is 0.45 newtons. And we know the units are kilogram meters per second squared. 1 Newton is 1 kilogram meter per second squared. So I'm just going to go ahead and put that in there. Instead of putting newtons in, I'm just going to put kilogram meter divided by second squared, because that is what a Newton is. 1 Newton is 1 kilogram meter per second squared. Now the mass of the ball is 0.45 kilograms, 0.45 kilograms. And then we're just solving for the acceleration of the ball. So I'll just put a sub b here. Now to solve this, we need to divide both sides of the equation by 0.45 kilograms. And then we should be able to easily solve for the acceleration of the ball. So you can see it's kind of nice. We have some units and some numbers that are going to easily cancel here. So let's work on the right-hand side. The number cancels as well as the unit, leaving us what it is that we want to solve for, which is the acceleration of the ball. Now the unit over here cancels as well as the number. So we're left with the unit 1 on the left-hand side, and the units we're left with what's left, meters per second squared. And on the right-hand side, we are left with the acceleration of the ball. So the ball is being accelerated, and from our picture, the ball is going to the right, so we can know that positive signs are to the right. So that's much we know. So now we know the acceleration of the ball. We can come down here and solve for it. We have 1 meter per second squared. And now we're able to solve for the acceleration of the astronaut. This is what we're trying to solve for here. So we need to divide both sides by minus 90 kilograms, just like we did in the previous example. And then we'll be able to cancel numbers and units easily. Let's start with the equal sign. So we'll carry our equal sign down. Notice our negative sign and our 90 and kilograms all go out. So we're just going to cross them all out. And we're left with acceleration of the astronaut on the right-hand side. And since it's a vector, I'll give it the little vector symbol. And I'll go ahead and give it the vector symbol up there. I forgot. So now we're going to drop off the kilograms, and we're left with a meter per second squared. And we're left with 0.45. And we're going to divide that by 90. And we have a negative sign. So there's that minus sign that's right there. So 45 divided by 90 is just basically a half. So we have our acceleration of the astronaut. And we know our units are meters per second squared. So 45 divided by 90 is just 1/2. So, or a 0.5. But we have to divide that out. So it's a 0.5 0.005 with a negative symbol. And so that is our answer. Our acceleration is minus 0.005 meters per second squared. The negative sign means it's in the opposite direction of positive, so that means that the ball is going, or not the ball, but the astronaut is going to the left.